Welcome students to Lesson 3 of Unit 12, Stoichiometry of Solution Reactions. The steps for solution stoichiometry, as with all stoichiometry: number 1, write the balanced equation. Number 2 is to calculate the moles of the reactants by multiplying molarity times liters. This is what we learned in the last lesson. Step number 3, if there are two givens, you must determine which reactant is the limiting reactant. Hopefully you remember this from stoichiometry earlier in the semester. Number 4, calculate the moles of the other reactants or products that are required. This is done by the conversion factor of coefficient of wanted over the coefficient of the given. And finally, you will convert the moles of the wanted to whatever unit they're asking for, and that's typically grams. So let's get started with an example problem. Calculate the mass of solid sodium sulfate that must be added to 250 ml of a 0.2 molar solution of barium nitrate to precipitate all the barium ions in the formation of barium sulfate. Also calculate the mass of barium sulfate formed. So we are given a volume and a concentration of the barium nitrate. We want to know how many grams of the reactant sodium sulfate are needed and how many grams of barium sulfate are produced. So my first task is to find out how many moles I would have of the barium nitrate. Moles are found by multiplying molarity times liters. The molarity of the barium nitrate solution is given to us at 0.200 molar. So 0.200 molarity times the volume is given in milliliters. It must be liters, so we're going to move our decimal point 3 places back to the left, and we're going to use 0.2500 liters. And when you multiply 0.2 times 0.25, the answer is 0.0500 moles. Okay, so the rest of this is pretty simple from here on out. Now that I know the moles, 0.0500 moles, I'm starting from moles of the given. I'm going to go to moles of this wanted here in one stoichiometric calculation, and then I'm going to turn around and go from this to this in the second. So let's start with our given. We just figured out the number of moles of the barium nitrate, so 0.0500 moles of the barium nitrate that's the moles of the given, so the coefficient in the balanced equation for every 1 mole of barium nitrate that reacts, I also will need 1 mole of the sodium sulfate to react with it. And since I want grams, the last step is to convert the moles of sodium sulfate to the grams. The molar mass of Na2SO4 is 142.05 grams. And now let's check our labels. Moles of barium nitrate cancel, moles of sodium sulfate cancel, and I'm left with the grams of sodium sulfate. And the answer is 7.10 grams of Na2SO4. Okay, now let's turn around. We know the answer for the amount of reactant necessary to react with this amount, this volume and concentration of barium nitrate. Now we want to go from the moles of the barium nitrate to the grams of barium sulfate. the precipitate from this that's formed from this reaction. So we have the same given, 0.0500 moles of barium nitrate every 1 mole of barium nitrate. We're producing 1 mole of barium sulfate. And a mole of barium sulfate has a molar mass of 233.40 grams. Moles of barium nitrate cancel, moles of barium sulfate cancel. I have left grams of barium sulfate. When I do the math and round to the appropriate significant digits, it's 11.7 grams of barium sulfate. And there you have it. The only new part in this kind of stoichiometry is determining the moles of the given from the molarity and the volume in liters. Multiplying molarity times liters gives us moles, and then we go right from moles of given to moles of the wanted using our mole-mole ratio, the moles of the wanted over the moles of the given, and then converting from the moles of the wanted to the grams using the molar mass. So let's take a look at another example. Calculate the mass of blood red silver chromate that forms when 50 mils of a 0.25 molar silver nitrate solution is mixed with 30 mils of a 0.250 molar potassium chromate solution. So what we see different here is that we've got information about the silver nitrate, one reactant, and also about the potassium chromate. We have volume and we have molarity from which we can determine moles. When you have given amounts of 2 reactants, that means we have a limiting reactant problem. So let's get started. Our first task is to take the volumes times the concentration of both of these solutions to determine the moles. So we have 50 milliliters. We're going to convert that to liters. We're working first with the silver nitrate. So I'm going to convert that 50 mils to 0.0500 liters. I'm going to multiply by its concentration at 0.250 molarity. When I do, I determine the moles to be 0.0125. That's the moles of the silver nitrate. And now for the potassium chromate, the other reactant, we're going to change these 30 mils to liters and multiply by its concentration. So 0.0300 liters times 0.250 molarity equals 0.00750 moles of potassium chromate. We're going to take each of these numbers of moles and determine how much of this silver chromate could be produced. And if you will remember, limiting reactant problems in the past, we're looking for whichever of these reactants gives us the smaller amount of product. That will be the correct answer, and that reactant will be the limiting reactant. So here we go. We'll start with the potassium chromate. 0.00750 moles of K2CrO4 potassium chromate. According to the balanced chemical reaction, for every 1 mole we're going for the silver chromate here. For every 1 mole of potassium chromate that reacts, 1 mole, see here, 1 mole, we're producing 1 mole, so it's a 1-to-1 ratio. 1 mole of potassium chromate, we can produce 1 mole of silver chromate. And then the question's about grams, so we want to use the molar mass. 1 mole of the silver chromate has a molar mass of 331.74 grams. 74 grams. And so, checking our labels, moles of potassium chromate cancel, moles of silver chromate cancel. We're left with the grams. And for this one, we get 2.49 grams of the silver chromate. Okay, so now let's go back with the other reactant, the 0.0215 moles of silver nitrate, and see what that will produce. So 0.0125 moles of silver nitrate. The ratio now, 2 moles will produce 1 mole of silver chromate. So we're going to have 2 moles of the silver nitrate, the given on the bottom, 1 mole of the silver chromate on the top, the wanted, and then the molar mass again. Every 1 mole of silver chromate has a molar mass of 331.74 grams. Check our labels. Moles of silver nitrate cancel, moles of silver chromate cancel. We get grams of silver chromate. And when you do the math, this turns out to be 2.07 grams. And since that's the smaller of the two, this is the answer. We can produce 2.07 grams of silver chromate. And since that is being produced, the smaller amount by the silver nitrate is our limiting reactant. Silver nitrate, limiting reactant. So as you see with both these types of problems, the only new thing is what you've learned about molarity times liters will give you moles. Once you have the moles of the given, you can go on to do whatever stoichiometric calculation you're required to do. Thanks for listening, and tomorrow in class we will practice many more of these calculations.